The countless stars in Earth's night sky represent just a small fraction of our home galaxy, a vast stellar pinwheel of more than 100 billion stars known as the Milky Way. When viewed from a distance, our galaxy appears immense, a teeming mass of tiny, glittering points of light, gas, and dust. Every morning, the closest star in our galaxy rises majestically above the horizon of our own planet, the Sun. Located just 93 million miles from Earth, our Sun is a 1.4 million kilometer ball of exploding gas, blasting out massive amounts of radiation at all wavelengths. This radiation, as well as radiation from other stars and from interstellar space, bombards our planet constantly. Fortunately, Earth's magnetic field and the ozone in our atmosphere form a protective cocoon around our planet that insulates us from most solar and cosmic radiation. Even with the protection of our atmosphere and magnetosphere, the effect of radiation on our bodies is apparent to anyone who has spent too much time outdoors. But what happens to our bodies when we leave the surface of Earth to travel in space or visit the International Space Station? Just outside the protective layer of Earth's atmosphere and magnetosphere, a few hundred miles above the surface, is a universe full of radiation. In addition to the solar radiation, X-rays, and gamma rays that we experience here on Earth, astronauts are exposed to even more dangerous forms of radiation once they leave our planet.
What we're concerned with for the astronauts is space radiation, which is cosmic rays that originate either from the Sun or from all the stars in our galaxy, so they're called galactic cosmic rays.
Galactic cosmic rays are bare atomic nuclei, some as heavy as iron atoms, accelerated to nearly the speed of light as they hurtle through interstellar space. Because of their high velocity, high mass, and positive electric charge, galactic cosmic rays cause tremendous damage to human cells. That's because when a particle of ionizing radiation penetrates the human body, it knocks electrons off of the atoms it encounters on its path through the body.
Wherever the particle goes, those cells are going to be highly damaged, which is different from other types of radiation.
Ionized radiation can also damage DNA, most often destroying both strands of the helix. The resulting damage and mutation of human cells and DNA can lead to future health problems like cataracts, cancer, and damage to the central nervous system. We are still learning about space radiation and its damaging effects on the human body. Until we know more about how human biology is affected, we do not know how many days humans can remain in space or how to protect them, especially during extended stays on the Moon or long-duration flights to Mars and other planets. One of the most valuable resources we have for studying the effects of radiation in space is the International Space Station. Research into the effects of radiation has been conducted on the station for several years. Some of the experiments that have been performed include studies on how radiation affects cells and tissue, medicines, and food. Before experiments can be flown in space, scientists on Earth must be able to conceptualize, create baselines, and develop models to test their theories. The Brookhaven National Laboratory in Long Island, New York, is the Earth-based analog of the International Space Station.
We can supply the kind of environment, not microgravity, not vacuum of space, but it's the closest you can get on Earth to mimic the sort of radiation environment that exists in space.
The Brookhaven National Laboratory includes a suite of particle accelerators and colliders. The facility is also home to the NASA Space Radiation Laboratory, or NSRL.
We take a particle beam that is either proton or heavy ion, and we accelerate it up to energies that are characteristic of the cosmic rays, and we use that particle beam to irradiate samples of cells and instrumentation, and we see what the effects of that space radiation is likely to be.
The types of radiation we experience on Earth, such as gamma rays and X-rays, are relatively low-energy forms of radiation. Although dangerous, they are not as difficult to shield against as high-energy radiation galactic cosmic rays, which can penetrate not only human skin and tissue, but also spacesuits and spacecraft. Radiation exposure on the Moon is very different from that in low Earth orbit. When astronauts travel to the Moon, they will leave behind the relative safety of the Earth's magnetosphere. Astronauts on the lunar surface face even greater risks from the effects of galactic cosmic rays and solar particle events.
On the Moon, you have no protection of the magnetic field, and you also have a very short warning, maybe just a few hours warning, so that the solar particle events become the major concern for the astronauts.
Scientists and engineers can partially shield astronauts from low to medium levels of radiation while they are inside vehicles and habitats on the lunar surface. 50 years of NASA research has shown that effective shielding from radiation consists of at least 10 to 15 centimeters of materials like water or polyethylene. But nothing can stop high-energy radiation like galactic cosmic rays. The challenge then becomes twofold: understanding the risks involved and finding ways to keep the risks as low as possible. In order to better understand these risks, researchers are studying the long-term effects of radiation on the human body. Astronauts currently spend an average of 6 months at a time living and working on the space station. To minimize radiation exposure, engineers and scientists have developed new types of shielding in the most frequently used locations. Materials that have high hydrogen content can reduce radiation exposure better than metals, such as aluminum.
On the space station, what we've done is implemented polyethylene shielding into the crew quarters of the astronauts, and this really reduces the dose from the trapped radiation, and when you do have a solar particle event, it would reduce those doses.
NASA is continuing to research different types of shielding for longer duration missions, such as flights to an asteroid or the surface of Mars. To be effective, the shielding must have enough mass to prevent the majority of radiation from entering the protected area. Shielding is only one element that will protect both current and future astronauts. Nutrition, such as antioxidants from fruit and vegetables, as well as medicines, may also play an important role. In order to protect astronauts and future space explorers, we must continue to learn more about the effects of space radiation on the human body. Understanding space radiation will not only help us protect the crew on the space station, but also those first humans that will take the next steps in the continued exploration of our solar system.